everyone. It's a pleasure and an honor to get to give 3 lectures here. So, yeah, so I tried to structure them so they're all and self-contained. So maybe I can start by giving a sort of outline of the general topic. So they all the common theme is that try to understand how local physics emerge in AdS CFT. And
sorry, can we start the recording?
Recording's on. Oh, the recording is already on.
Good. And is my microphone correct? Can you hear?
Can you hear the microphone? Yeah. Okay.
It's good. Okay. Yeah. So general term, general theme is to understand locality of the bulk physics, and we'll be doing this in various setups. So maybe let me start by some general picture. So I think this one of the very important thing we learn in AdS CFT is that so I'm going to draw like the picture in the empty AdS, where this is the cylinder and this is time going up. So this will be the sphere and d-1, and the idea of AdS CFT is that you have a kind of a CFT in d+1 dimension. Sorry, in d dimension that's related to AdS space in d+1 dimension. And the idea is that you can think about the ordinary quantum system that exists at the boundary of the cylinder, and it's supposed to be equivalent to a gravitational system that fills the inside of the cylinder. Okay? And one of the things that's interesting is that there are things that we know, strong results that we know about any conformal field theory that we will not necessarily know about gravity, even when the theories is strongly coupled. And one of the examples is causality in the CFT. So for example, if you hit the field theory with a hammer here at time 0, the light and the sound from this are going to propagate at some speed, but there's no way that then any information about this can get across the other side of the cylinder before a time, say pi in units of the radius of the cylinder. And this is a sharp statement on the CFT, is that the commutators of operator at the boundary is exactly 0 when they are space-like separated from each other. It's true even if the CFT is a complicated, strongly interacting thing that we don't really know how to analyze. We know that it's going to satisfy that. Okay. And
saying that the correlation functions in Euclidean space have only coincident point singularities?
Yeah, okay. The question is, how does that relate to Euclidean space? I think you need a bit more than that. So if you start with a Euclidean theory that has rotational symmetry, naively you take you have something like this, and then you take z goes to it. This will look like a function of Lorentz invariant distance, and you might think, well, probably I'm only going to get singularities after I continue after we rotate. I'm only going to get singularity inside light cones and so on. But actually, this does not follow. And the extra thing that you need, in addition for rotational invariance, is a notion of reflection positivity. Positivity in Euclidean, which is the thing that maps to unitarity in the CFT, in the QFT, in the Lorentz sensing answer. So if you don't have a notion of unitarity, it's actually possible to find example of correlation functions that 4-point functions that are rotationally invariant, and you can Wick rotate, but you try to Wick rotate them and you find singularities at weird places. And effectively, these positivity properties answer that operator product expansions and various basically the answer that you don't get singularities at wrong places.
No. Is there a simple example where one can see this?
I think so, yeah. So let's see. It actually happens all the time in celestial holography. You take the scattering amplitude which are function on the angles on the sphere. they don't have nice necessity property. Let me see if I can find an explicit examples. Okay, there's no. I think we can find one later.
Yeah, okay,
But yeah, I've seen such a. There are definitely examples of Euclidean correlation function that are rotationally invariant, but you cannot Wick rotate sensibly. The thing that answers that you can actually Wick rotate is the reflection positivity.
These papers by Hartman and friends studied this in detail, right?
Uh-huh.
The causalities papers, the ones that said that
Yeah.
on the second sheet the singularity will go to the wrong side of the right one. And with
Yeah,
the,
but you really need unitarity to prove to make
Yeah,
these things. Yeah.
yeah, that was
Yeah. Yeah. Great. Yeah. Yeah. So in the context of AdS CFT, I think this is just this fact is a very major result, because it basically tells you that inside the bulk you must also have some notion of relativity. So for example, if inside the bulk you could send information in some kind of instantaneous action distance in the bulk, then you could send a signal here to the boundary that influences this guy and then goes here, and then it will come out on the other side. The information will come out faster than light on the other side. So you'll break CFT causality if you add instantaneous action distance inside the bulk. And that argument works because, in fact, any geodesic that cuts through the bulk, actually end up exactly at the other side of time pi in AdS geometry. So that's a property of the AdS geometry that, like, you might have thought naively, if you think about the cylinder, you should be able to go faster to go through than to go around. But the geometry of AdS is exactly such that it takes the exact amount of time, no matter how you go through, to the antipodal point. And yeah, but this picture is very powerful because it doesn't have to be only true in a vacuum. You could apply it in an excited state. So suppose I create some excitation here, and it's going across. So it must also be true that it's still true that this commutes with this in this excited state. So whatever this state does, it can only somehow slow down signal and not speed them up. Okay? Then we can say absorb this guy here. So it's a very, yeah. So inside the bulk, there can be no, my eraser is there. So there's an exact statement that colloquially says that there can be no, we cannot send signals faster than lights. Even in the bulk.
So in AdS, the statement is, you could make the statement purely on the boundary, in the sense that there's light code on the boundary that you can observe. But in flat space, if we were trying to make a similar statement in flat space, then we would have to sort of say that if you filled out that flat space with the asymptotic region with a flat space, then you cannot send signals faster than the light ray that would go in that.
In the vacuum, yeah.
There's no boundary for that, right?
Yeah. Yeah,
so more complicated statement in flat space.
Well, so in flat space, okay, let's see. So there's a sharp statement in CFT, that's exact. In Minkowski space, if you try to make sense of this statement in AdS, you have a sharp statement from the CFT. In empty Minkowski, then there is a sharp statement involving. You can make sharp statement involving S matrix. But these S matrix are telling you about small perturbation of. So imagine you have to imagine that you have empty Minkowski space everywhere, and then you make a little perturbation of it like this, and then you compare the time it takes to get across to the time it will take if there was not this perturbation. That is what S matrix analyticity will tell us. Yeah. And it's a little bit less clear why that would be true. On the other hand, part of the main goal of this first lecture will be to show that actually, whenever you are in a situation where in CFT you can localize to a small region of the AdS space, you get the CFT constraint exactly become this S matrix constraint.
Sorry, what was the S matrix constraint?
the S matrix, it will be a constraint. Actually, this I will study it more tomorrow. But the S matrix constraint is essentially an analyticity of the S matrix and some boundedness property.
And suppose in flat space we wanted to make a statement that went beyond small perturbations.
Yeah.
So would the following statement be true?
Mm-hmm.
That consider any asymptotically flat geometry.
Yes.
Could be really different from flat space at the minute.
Yeah.
Far away it's asymptotically flat.
Yeah.
Now, at least in 5 and higher dimensions, this guy goes at infinity goes so fast to flat space that there's a well-defined notion of just filling out that asymptotically with flat space.
Yeah.
And now you can compare rays of light in this fake space with what it would be in the middle.
Yeah.
And demand never always goes.
Yeah. This is what the S matrix thing tells you, because you can, essentially the S matrix language, the sort of tough experiment you're describing is I can start from particles that are well separated and small perturbation of Minkowski, and then I put them out together and they make a black hole in a very complicated geometry, but still there's an overall flat space structure asymptotically that I can use to set my clocks.
And this is much less clear in 4 dimensions, right?
In 4 dimensions, it's a little bit less clear because of infrared log divergence. So what happened in 4 dimensions is that this is to some extent, a lot of the physics is just in F equal ma here, so let me mention it. so in 4 dimensions, if you throw 2 particles at each other and they can interact gravitationally, this attractive force that goes like -1 over r square. So minus gmm over r square. So, and r is approximately vt, right? If the relative velocity is a function of time. So you integrate this, you get that the change in the velocity caused by the force goes like 1 over r. And then you integrate it twice and you get that delta x goes like log r. And what does that mean? It means that if you start a particle at some time t and you aim them so that they will arrive at the origin so you aim them in the scattering experiment so that they will hit, you will naively think that they hit 0 they hit each other at time 0. The time where they hit will actually be displaced by an amount that goes logarithmically like log t times gmm. So you get the time shift of this type. And funnily, in Newtonian physics, it's a time advance. So the particles attract, so they hit faster than you'd think. But interestingly, because of redshift factors, for relativistic particles, it's a time delay. And because it's a delay, it's compatible with this picture. So it's a large delay, and it's fine. And okay, one of the things we will see is that, I don't know how much we'll see, but okay, now one thing that comes out of this analysis is that this log becomes log of RADS times the energy you're looking at. So in ADS space, you get this infrared log. I think I'm not so bothered by this, but it means that all the results we get in 4 dimensions have an infrared log in them. But because this log has a clear interpretation, it's just like the size of the experiment you do to test your causality. I don't think it's a real issue, but it weakens a little bit the result. But this is log of the size of the experiment. How big can that be? How big what is log of infinity in physics, right?
I was thinking of a slightly different effect, which I'll shut up after this.
No, keep going. This is great.
It was that, see, the Newtonian potential, so changes in the metric in 4-dimension scale like 1 by r.
Yeah.
So at some distance r, if you take some sort of holonomy around infinity, you get a non-trivial holonomy.
Yeah.
So it's less clear what it means to fill out infinity with flat space. So even the question of what it means for something to go faster than it would have gone in the absence is less clear to me. How to state that is less clear. Whereas in 5 dimensions, because the potential goes like 1 over r squared, the holonomies are zero. And so it's very clear.
Yeah. I think this is part of, I think what you're referring to is a question of exactly how you synchronize your clocks at infinity.
Yeah.
And
so I would say that AdS makes the picture really clear because infinity
Yeah.
Okay, in 5 and higher dimensions in flat space is also sufficiently rigid.
Yeah.
4 dimensions feels less rigid to me. Let's give it a try.
Yeah, it does seem to me though that if you imagine that and in a vacuum state, I do think you can send by sending light across the bulk. By sending light across Minkowski space, I think you have a canonical way of synchronizing your clocks.
Okay, we get it.
Yeah. But yeah, when you have particle in that, when you have a particle inside, it's different.
Right.
Yeah. Great. Yeah. So the general goal of these lectures will be to explore the implication of this thing. So yeah, the first lecture will be about relating those two cases that we understand sharply. This first lecture actually will probably be the hardest one for me to give, because I've never given lectures on this, and part of the arguments are very technical, but at the same time I want to get the general ideas across. So we'll see how that goes. And then the next one here as a sort of more straightforward starting point, and the last one would be more like a talk type lecture where I'll discuss some idea if you have a completely general bulk geometry and you like to just somehow measure the metric by doing scattering experiments, how would we actually do it? Okay, so that's going to be the idea. Okay? Great. But yeah, don't hesitate to ask question, anyone. It's very helpful. So, yeah, so we want to explore the space of theories that are consistent with this notion that you cannot send signal faster than light. And you know, even when it cannot be, I really want to emphasize it's about local physics. So you know, as long as you can do tough experiments that test causality, you know, the curvature universe is not very large on the solar system scale, and certainly we can make colliders that test causality on the planet, right? So a lot of this is really about the local physics. Okay. But we're using this asymptotic statement as like an anchor to turn them to math. So we want to explore, you know, what is a space of theories of gravity, for example, that are compatible with this notion. Can you modify Einstein gravity or not? That's a sort of a general question. One thing I want to say, a qualitative thing I want to start with, is that just from this notion that you cannot send signal faster than light, you sort of get for free a lot of the architecture of quantum field theory and particle physics. So, and that's going to play an important role today. So I want to somehow just explain this qualitatively first. And the sort of cartoon here is the following: that if you imagine you have two electrons, it's going to be time, it's going to be x. And imagine you have an electron whose world line is like, it's just sitting there at the origin, but then at time 0, like you kick it, so it follows some path. Okay? And then some other distance, you have you have another electron that's just sitting there. And its point in life is to measure the force from the first one. Okay. And of course, you know that once you move this electron, the force law will change. Like it's closer, 1/r² gets closer. On the other end, this notion tells us that there should not be instantaneous action to distance, so the force doesn't change instantly. In fact, the force only changes on the future light cone of this point, right? There's a retarded response. So here the force changes here. But what does it tell us? So the information. So that means, okay, the information that the particle has moved and accelerated only gets travel the speed of light. But also, it's not just information that travels here, because this force here has changed. But this force here, I could use it to act on this electron and give momentum to the electron, give energy. So this thing has to carry in along with information, there has to be energy and momentum that are carried. So this kind of abstract notion of info is really actually must come along with energy and momentum that are very sharply measurable. And that is basically why whenever you accelerate a charge, it has to radiate. Because if the force depends on, if the force is affected by by changing the position of the particle, it has to be that it sends a wave to tell, so the wave exists to tell the world that the electron has changed. Okay? So basically, this general principle tells us that all forces in nature must be mediated by waves in some fields. And in quantum theory, when you account for the notion that a wave with a given frequency only has discrete levels of energy, quantized by units of h bar omega, you get that actually this wave is made of many particles. Okay? So basically, the basic architecture of quantum field theory is forced on us by this principle. And so that means that somehow, whatever happens in the bulk, we should be able to understand from, like, if I had an electron in the bulk, an electron here, and they interact with each other, whatever happens, I have to be able to understand these interaction by some kind of Feynman-like diagrams, where somehow the force between them gets broken into two processes, where it's related to a different process, where somehow I move this electron, it accelerates, it emits radiation, and then the radiation gets absorbed by the other. So all forces you must somehow be able to understand in terms of simpler building block, where you emit and absorb particles, radiation. Okay, so yeah, and somehow we will yeah. So to start to understand the local physics in the bulk, what I will mean is that we can start to see that interactions in the bulk come from Feynman diagrams. That's essentially the goal of that question.
Are these arguments only true of regions of space-time which are causally accessible to the asymptotic boundary?
Yeah. Yeah. And specifically, we'll only make very sharp arguments about empty AdS, precisely because we need this very special configuration where things are separated by pi. So the line of arguments we'll use work in empty AdS. One thing that I think would be very nice to understand, is a very important question, is that it's a basic fact about the equivalence principle in the bulk that it's the same local physics at any place. Doesn't matter how you change the geometry, in some local coordinates, the local physics should be the same. And so in some sense, once you constrain the interactions in empty AdS, you're morally constraining the interactions in any background. But in order to directly make the argument in any background, we don't know how to do it. Yeah. So, maybe we can do something funny also. I can ask, suppose you don't care about this principle. Suppose you don't care, you're happy with some incidence action to distance. Maybe, if somehow the world, the laws of nature allows singles to instantly propagate across distance of 10 to minus 20 meters. Like, that wouldn't change our everyday, so why should we care, right? So suppose we don't care about instantaneous action to distance. I claim that it's actually very easy to solve the problem of quantum gravity. Let's be more extreme. Let's forget about the 10 minus 20 meters. Suppose you don't care at all about adding instantaneous action distance. Let's try to write down a theory that has quantum and gravity in it. I think this is very easy. Anyone has a suggestion? How will we start? We want to have gravity, so I know. What should we start with? Let's start with maybe Newton's law, right? Right. So we can write like quantum mechanics, say p squared over 2m I, sum of all particles in the wall, kinetic energy minus sum of I and j, g, mi, mj over xi minus xj. can write down a non-realistic theory, and it's a quantum theory. It's gravity. What more you want? Yeah. It's not a great theory, right? Hey, what's wrong with this theory? Anyone, feel free to say. I'm sure you can find things that are wrong with this theory. I want people to participate a little bit. Don't be shy.
If you care about instantaneous,
Yeah.
then I mean, even without that, you're saying something, find something wrong with this theory.
Yeah. Yeah, first of all, yeah, you don't really need much relativity, so we didn't put a lot of relativity, but you can probably improve that by adding a P4 or something. Like you could correct this to make it more relativistic, right? But yeah.
Even for two particles, you're saying something's wrong with this theory?
I mean, the same issue that arises when one does constrain.
Yeah.
Okay.
Yeah, I mean, I think you will need eventually to have a framework where particles can be created or absorbed. So you'll be forced to you'll be forced to have some kind of QFT notion. So let's improve that and add the things that A dagger, A terms out. Okay, let's add by n things that so that roughly we can reproduce a standard model. And what else are we missing? We get the standard model. We got gravity. There's a lot of experiments that this violates, right?
You're asking you couple standard model to non-relativistic gravity.
Yeah, this looks a bit weird, right? Yeah. So probably we should make this a little bit more relativistic. But yeah, so this model doesn't have gravity waves for one thing. Right? So they're experimentally observed, so that's bad. So let's add I don't know, some Hamiltonian for gravity waves. Let's add it by hand. Yeah. And maybe I don't like this force law. Maybe let's just replace this by some potential, like psi minus xg. Right. And actually, now is the homework that's a little bit harder. But suppose you wanted this in this framework. Question is, can you actually fit all experiments that have been done so far? Can you fine-tune all these coefficients to correctly get the correct description of gravity waves, the correct standard model up to, distances of 1/10 TeV that have been probed at colliders? Can you actually do that? And yeah, of course, you can rewrite the standard model in Hamiltonian force. It's nothing. It's a good exercise to do it if you really want, but yeah, in principle, you could do it. I think that the thing which I find most unsatisfactory with this approach is that it's basically curve fitting. There's no predictive power. So for example, you could decide that the potential is like 1/r up to whatever distances we've tested, and then it can be anything you want. Right? And you could decide that particles look like points up to 10 to 20 meters, but after that, they actually are little elephants. You can say what you want, and as long as the elephant is smooth enough, this theory will be UV complete. So there's no predictive power. Well,
there's always freedom to change
yeah.
the potential.
Yeah, exactly. So in Newtonian physics, what happened is that this V of R is measured from experiment. And there's a lot of structures that are somehow predicted. So energy conservation, like the laws have to be compatible with some general principles. But in principle, in Newtonian's gravity, the potential can be anything, can be V of R up to whatever distance has been measured, or some microns. And then you can change it to whatever you want, and the theory doesn't care. So a lot of the ingredients in Newtonian physics have to be just taken empirically from experiments. And field theory does a bit beyond, because the form of the V of R is tied to the fact that you emit and absorb gravitons, and the basic structures for emitting and absorbing graviton is fixed by local Lorentz invariance. So once you assume that once you realize that the force is mediated by exchange of gravitons, it cannot have a different functional form than that. So this principle makes theories much more predictive. Yeah. Otherwise, you are always looking for is physics completely different at the next energy scale that we've not proven, that we've not probed, or so it can be anything.
Can there be something like Mills inequalities which will kill it? Some sort of.
Well, as long as you respect quantum mechanics. As long as like if there's a Hamiltonian here, you make this potential smooth enough at short distance, that will be a perfectly unitarity evolution, and then if it respects the axiom of quantum mechanics, you won't run into Bell-type paradoxes. I'm not sure that's what you had in mind, but yeah. I think it's actually this is a challenge for the future. Is that okay? Here, but this motivates the game. We're really going to take this notion seriously and try to find its implications. But part of the reason is that there's no other game in town. If you give up this, I don't know. There's no. I think at the moment there is no.
No, but you said even with this model you can even satisfy that up to very short distances, right?
Yeah, but we're going to assume that it's exact. Yeah, exactly. So the game we will play is that we assume that this notion you cannot send faster than light is actually true. Like it's not even like it's not that the commutator here when it's your slightly space-like is small. It's exactly 0 for any epsilon. So we're going to try to assume try to work out the consequence of having this very sharp notion when you can make it sharp.
How can this be even approximately modeling that? Because they say that some planet, some sun disappears, the Earth will fly immediately and so on, right? Where is this even approximately? How is that idea even approximately built into this model?
Yeah, well, this model will have to be much more constrained. So we're not going to take this approach.
Yes.
Yeah, I'm not suggesting you do that. Yeah.
Kill it immediately?
Why? Yeah.
Why doesn't this notion that it cannot even approximately?
No, but
that idea. I mean,
but this no.
If you could make it so that 10 to the minus 20 meters.
No, I think using this framework and fine tuning the coefficient, you could get to a situation where you cannot send single faster than some epsilon. And then it's only ruled out. It's not ruled out experimentally. It's only ruled out by. I think it. Yeah. How should I see it? You don't see that?
That you can make it approximately obey that law.
Okay. No, here I'm not saying anything very deep. Just take the standard model and write it in Hamiltonian form. And then in Hamiltonian form there'll be some potentials and things like this. Just modify them slightly.
I think he's saying that the gravity wave would be one of the fields.
Yeah, the gravity wave would be one of the fields.
And then this is interaction with the wave and the wave.
Yeah. But in addition to the force.
This force is an instantaneous force there, right?
Okay. Yeah. So once you add this, you will have a lot of force from this, and then you can have just a delta V here. So you can add a little bit of extra instantaneous action in the distance on top of what you get from gravity waves. You can think of it like that. Thanks. Yeah. This is so I think this is maybe the only message I would say is that sometimes you see people trying to model violations of causality and so on by field theory, trying to write down non-local field theories and things like this. And I think the basic message is that, come on, we should try to be more creative than that. Like, if you're going to have an instantaneous action distance, why are you even doing field theory? That's my main message.
The usual issue that people point out is this particle production, right? If you just stick to quantum field theory and
Yeah, then you need particle, yeah, you need particle production.
So
Yeah.
you want to highlight a similar issue that concerns gravity. If
Yeah.
one can have that. But isn't like
Yeah.
Hawking radiation or something like that?
Yeah, but
Formation of black holes, if you go into that,
Yeah.
it kind of sounds like that, right? That you have
Yeah.
a bunch of gravitons and being produced.
but even there, I think that this framework is just too flexible. You could have the Hawking radiation by hand. I think you could, yeah. All right. Okay. So what are the key ideas for how we actually do it? I'm doing my best to erase clean. There's always a little reminder. Okay. Great. So, okay. So the basic constraint mathematically we'll look at are this expectation value where I put some operator. I'm just going to write 1. And I'm going to take a commutator of 2 operators like this. And this should be equal to 0 in 2 and 3 space-like. Okay. The first thing I want to explain is that this equation is an equation that all of you have seen in some form, is a conformal Bootstrap equation. And the reason it is that if you insert a complete basis of states here, and in the CFT, the states are labeled by local operators, by the state operator correspondence, there's this nice fact that whenever 2 operators act on a vacuum, the OP converge. So this statement you can draw as follow. So if I draw 1, 2, 4, 3, this you can draw in this form, where this diagram stands for the sum over all states in this OP channel that exchange 1 and 2 and 3 and 4. And on the other hand, when you take the other term of the commutator, you exchange in a 1, 3, and 2, 4 channel, which gives you the other diagram. So this famous Bootstrap equation is really exactly the statement that space-like commutators vanish.
So it's more, I mean, Euclidean space, I understand this convergence
Yeah.
of OP with the spheres and that
Yeah.
kind of argument.
Yeah.
So what is the argument for this?
Yeah. Great. Yeah, so let's discuss a little bit OP convergence. Yeah, so the starting point with cleanness is in Euclidean space, as you mentioned. And I'm going to use some very nice coordinates in Euclidean space. I call them x and y.
Oh, I see. You just go to
Yeah. So suppose I put 4 points. I actually, okay, I'm skipping a lot on conformal geometry. But one of the nice things about conformal geometry is that when you have configuration of 4 points, you can map them. You can translate the point. You can rescale the configuration. So you can assume that 2 of the points look like this. And you can also still do conformal transformation, which stretch the other one. And you can actually assume that the other 2 will look like this. Rho minus rho, where rho is x plus iy, some complex number. Okay. So in Euclidean space, you have a picture like this. And the basic notion of this operator product expansion is that you're inserting a complete basis of states on a sphere that separates the small one and the bigger one. And then so this is the state. This is the complete basis of state is basically inserting complete basis of state on the path integral on this, yeah, because the states on a sphere are exactly the local operators of the theory. Okay, and that gives you, if you do it without thinking about descendants and all of this blah blah, this gives you basically a correlation function as a sum over scaling dimension and spin of some coefficient times rho to the delta minus 0 over 2 times the complex conjugate delta plus 0 over 2. And A, I'm not saying anything very deep. So you see rho bar as a power delta, which is a scaling dimension. So that's the norm of rho, which is a power that's set by the norm of rho. And the other thing is that if you write rho equal x of, let's call it like this, x of I theta, this thing here would become the absolute value of rho to the delta times x provide j theta. Okay, so by having this plus j and minus j pattern, you make j conjugate to angle. Okay, and this angle is very literally that angle. Okay. So in Lorentzian, so yeah, and the nice statement is that this sum, if you evaluate this sum on the real axis, it becomes a sum of positive numbers by unitarity. So these c's there are all positive. And if you evaluate this sum on the real axis, it's absolutely convergent. And you can even bound it using OP and other channels and so on. So this is absolutely convergent sum. And what this tells us, the fact that this is absolutely convergent when rho and rho bar are real and positive, tells us that actually, and the coefficient are positive, that tells us that the sum actually converge for any complex rho and rho bar independent of each other as long as they are less than 1. And at 1, it converges conditionally. So in order to go to this statement here, to go to Lorentzian signature, so if I draw the Lorentzian cylinder, now I can draw the same, very similar thing. I have these two configurations in the past and these two other configurations in the future at some points that are separated from each other. And the important point is that the radius, when you go to Lorentzian signature, what used to be the norm of rho becomes x of I times t. So you wick rotate, to go to the Lorentzian cylinder, you wick rotate the radius. And when you do that, the important thing is that there's a little I epsilon here. And because of this I epsilon, it means that the operators that are inserted in the past are a little epsilon away from the operator in the future. So basically, if you have two operators that act on the vacuum and two operators in the future, then they basically, when you calculate a correlation function like this, let's call it like this, O1, O2, O3, O4. Let's say it's not a time order function. It's really literally a Whiteman function. The I epsilons will be ordered in such a way that rho 2 is equal to rho 1 times 1 minus epsilon, and so on. So they order such that they strictly, I guess, okay, I'm going to get backward, but...
You're saying the Euclidean time gives the ordering of the
Exactly. So the little epsilon in the Euclidean time that gives the operator ordering gives you the size of the rows, and basically, yeah, 3, 1 minus epsilon. So this is Feynman I epsilon. So basically, this converge thanks to this Feynman I epsilon, which means that this sum converges as distribution for yeah. So it converges absolutely when it's less than 1, and it converges 10 to the I epsilon, which means it converges as a distribution. Converge as a distribution for Whiteman function. Where rho is 1 minus epsilon. Yeah.
So if these operators 1 and 2, if they were time-like separated,
yeah,
then also this continues to go.
Yeah, exactly. So they can be time-like, they can be anywhere on the cylinder. And so for example, in Lorentzian signature, the analog of this cartoon here, you can draw like this. And this would be x and t. And so we can take a conversion that's at -1 and 1. And then something here at a rho and a minus rho. And you see that I've crossed this like cone, and it still converge absolutely.
So, could I translate what you said to the following? That since the Euclidean time gives the ordering of operators in the Lorentzian space,
yeah,
the earlier operators are in a smaller disk.
Exactly.
And later operators.
Exactly.
Larger,
Exactly. So exactly. So the operators that are on the right of the operator product are the inside of the disk, and the ones on the left of the operator product are sitting on larger disk.
And therefore,
yeah,
you just use state
exactly.
operator mapper.
Exactly. If you wanted to directly do the OP between 1 and 3, you will have a problem because you go from a small disk to a large disk to a small disk, and then you cannot draw a picture where you answer the complete basis of state. So it's only when you separate, you have two things acting in a vacuum that you can do that. You can OP them. Yeah. And actually, it would be quite important that this OPE makes sense in Lorentzian signature in that sense. And the other thing that we can see from these is that, let me see, yeah, great.
Because here, from this commutator, space you've got conformal Bootstrap, space-like separations.
Yes.
And like in EP, it's if this conformal Bootstrap holds always.
Yeah.
So we will go back. So how come this commutator arises?
Yeah.
The basics.
So can you say, so yeah, so in Euclidean you can always do, yeah, in Euclidean this always works.
Yes,
it's always true.
Back and get the commutator to be valid to be 0.
Uh-huh. Yeah, so that's a statement about, yeah, so what does it mean that the commutator becomes 0 in the, yeah, so if you start from the Euclidean, yeah, so in the Euclidean you have this equals 0. Then when you go to Lorentzian, the fact that this commutator continues to be 0 means that,
So the question was, if you go from this line of Bootstrap to the correlation function,
yeah,
you get that the correlation function vanishes with the commutator.
yeah.
But why it should vanish for Euclidean? Why don't for its usual?
Yeah, in Euclidean you will not write commutators. Yeah, in Euclidean space there's no notion of commutators. Because you cannot do backward evolution of Euclidean time. So this is a direct Lorentzian statement, which when you evaluate it on points that are space-like from each other happens to be the Euclidean statement. But you cannot write commutators directly in Euclidean space. Yeah.
And sorry, and the same, just continuing on Raman's question, the same kind of argument. Now suppose I take 3 and 2 to not be space-like, separated in Lorentzian space.
Yeah.
So once again I get this minus this, but now is equal to something else. Right?
Yeah, and it will fail because there will be some extra phase or that don't add up.
Yeah, but would that equation, suppose I know what the commutator is, that gives me an equation, would that be of interest ever? That instead of this minus this being 0, you get this minus this is equal to something you might know.
Yeah, I'm not sure. But what we'll do next is study other commutators where you commutate 1 and 2 and 3 and 4, and these will have nice OPs for those.
Okay.
But not at the moment. Yeah. So let me introduce the kinematics that will be of interest. Okay. Yeah, another thing that is an untrivial fact that you can derive from this simple statement about convergence of series is that, let me erase this commutator, is that if you take, okay, so this is going to be a space-time diagram, so time here, x go like this. So if you take configuration, I'm going to take this guy and this guy to be space-like for a reason that will be clear shortly, and then this guy. Suppose I take a configuration like this. And okay, I said that if 1 and 2 are applied directly in a vacuum, you can apply OPE. Another thing you can do is that you notice that, say this guy here, let me call this guy 1 and 4, 2, 3. Notice that these guys commute with these guys. So in this configuration, you can always do the OP of 1 and 4. So that OP always work. And so the OP in 1,4 channel I think I need some other ingredient, which is that you can study this for various operator orderings, and it will converge for all the operator orderings. So one can be before 4 or after 4, it will not matter. And the difference between different operator orderings will be effectively whether you some of this phase here becomes okay, let me sorry, I have to improvise a little bit here. So what I want to say here is that there's a ordering where, okay, let's list what the 4 orderings do, and we see that there's some orderings that are particularly simple and others that are complicated, but the complicated one will be bounded by the simple one. Okay. Great. So the OP in the 1,4 channel. So I'll just write the vacuum once. So one thing you can do is to have 1,3 followed by 2,4. Okay? Which is the same as, because 3 commutes with 1,4, is the same as 1, then 4, and then 3 times 2. Then you can insert the complete basis of states and this converge. This works. And so you can do this OP. And this has a very nice interpretation. It's taking a state in the past, 1, 3 in the past, and evolving it to the future. So this is basically like the time order correlator. Okay. There's another thing you can do, which is just the reverse. You could put the 2,4 here and the 1,3, and that's going to be like the anti-time order correlator. And the other ones are a little bit less intuitive. So one thing you could do is you could take you can literally take, you could take 1 and 2, and then 3 and 4. 1, 2, and then 3, 4. So 1, 2, which is the same as, so I start with this and I finish with this. So now for 1, 2 I'm going up, and the other here I'm going down. Okay?
I didn't understand how you could take this. Physically you start with, as you said, reading backwards, 1, 3, 4, 2.
Yes.
And then what manipulation allows you to go to that 1, 3, 2, 4? Sorry, what manipulation allows you to go to those 1 and 2 together? Did you say you could take 1 and 2 together?
Yeah. No, this is a different order.
Yeah, so act 1 and 2 on the vacuum. You're allowed to write down any operators any order you want.
You can do whatever you want, but
yeah.
Is that this configuration?
Sorry?
Is that this configuration?
Yeah, the points are still exactly the same place.
Oh, you're just choosing different order.
Yeah, exactly.
Different Euclidean orders.
Exactly. Exactly. So we have this configuration here.
That's like a Bootstrap order.
Exactly. So this is like the Rindler ordering. Yeah. So in Rindler space, people would call this the time order and the OTOC. But in terms of physical time, it's backward. Yeah. What I want to say is that this guy here, you can use the OP in the 1-2 channel. In addition, so this guy here is, if you use the OP in the 1-2 channel, so that's not actually what I want to do. Let me try to say it better. Okay, yeah. I need one result that is nice, and maybe it's not well known, so maybe I would state it. So it's also nice. So there's something that is cool on the cylinder. Okay. So we need to exit the Poincaré patch temporarily. So remember that in conformal geometry, the space-time is embedded a set of points that is space-like from space-like infinity. So that's our space-time. Minkowski space is this. Right? This is the Poincaré patch of space-time. one thing which is a fact that is nice, which is then when a single operator acts on the vacuum on one slice, let's say I put an operator here. There's a point here that I call, say, x. Let's call it this point 1. Okay? There's another point that has the exact same coordinate as this point in Minkowski space, but since it's a second sheet. So we can write, there's another point here, that's the antipodal point. Let's call this infinity plus 1. And there's another Poincare patch that goes like here. And there's another point here that is, let's call it 1 plus. It's another point that is like here.
Pi shift alongside.
Exactly. So it's shifted by pi in time and rotated by pi. It's actually a spatial reflection.
And an analytic coordinate, it's just shifted by pi.
Yeah. And the statement is that when one operator acts on one primary acts on the vacuum, you can shift and it's the same thing. Up to a perfectly predictable phase, which I forgot. It is something like x plus I pi delta or something. Put it in quote. So this is discussed in a paper by Simons-Duffin and Kravchuk. They needed to play this game of moving in order to close the algebra of conformal transformations. And you have this nice result here that when an operator acts on the vacuum, it does something like that. So why am I describing this? It's because in this configuration, 1 and 2 are acting next to each other in a vacuum. And in this situation, it looks like 1 and 2 are far from each other. But in reality, 1 is very close to the image. The image of 1 is very close to the image of 2. So this configuration here that I drew.
So theta would be like h. In 2 dimensions, this would be like the holomorphic dimension.
Yeah.
Because you're just moving in a holomorphic direction.
Yeah, I think you're right. It's delta minus j. Yeah, thanks. Okay. So yeah, if I had color chalk, what I would draw is that effectively this configuration here, this 1, 2, 3, 4, is effectively, you can think of this 1, 2 as being close to each other, and this 3, 4 as being close. So this is a very boring configuration, but there's no scattering. It's just basically 1, 2 times 3, 4. It's a very simple configuration. Okay, so no scattering. And you can do the same for the other configuration.
Can you explain? I didn't understand. What was this last statement?
Yeah, because so let's see. So this is approximately equal to, this is the same as 2 times 1 plus. So you can move this 1 to be effectively here. And you can play the same here and put this 4 here to be 4 minus. And then it factorizes. So this correlation function nicely factorizes in this limit. So here I'm assuming that I'm taking a large boost, so the picture really looks like this. So as this goes to infinity, along a limit of large boost, this 1 and 2 become the same point, and shifted by exactly 1 patch, and therefore you can factorize the 1, 2 like this. Okay? So this is simple and no scattering. And something else we can show, which I will not show here, is that in the limit it goes to that which is bounded, but even away from the limit you can bound it from the other two. I will not discuss that here.
The Regge limit is not this with a different ordering. What is that ordering?
Yeah. So all of the So Regge. Yeah. Let's talk about the limits that are going to play an important role. Okay. So the Regge limit is that you apply a large boost. So on this picture of the cylinder, it means at this point, if this goes to 0, the other point will approach the antipode point pi. And same here, this approach, the points approach this regime, this limit. So you apply a large boost in one direction to 1 and 2, and you apply a large boost in the other direction to 3 and 4, so like a large relative boost. But you can do this for any operator ordering.
Yeah.
But there's one operator ordering which gives you something very boring,
Yeah.
but there's 2 operator orderings which just give you something interesting.
The original thing, the time order was the Regge limit.
Yeah.
And that was time ordered in Minkowski space.
Yeah.
Time ordered in Minkowski space. Yeah.
Yeah. So I'm just going to use an analogy here that is actually quite useful. which is that if you think loosely speaking at this amplitude, you go from 1, 2 to 3, 4. Like there's no S matrix in the quantum field theory, in the CFT, but you can still think of this as a overlap between some in state and out state.
Which ordering are you talking about?
The first one,
Okay.
1, 3, 2, 4.
Yeah.
So this guy here kind of looks like a matrix element of the S matrix. Like it's in quote unquote, think of it as you pair state 1, 2, you evolve it to the future, and take 3, 4. So the S matrix is not a well-defined matrix, but it still makes sense to take matrix element of time evolution.
Well, I didn't understand the 1, 2, and the 3, 4. I thought it was
1,
3,
3, 2, 4. Thank you. Thank you.
And this is almost, right? You want to move them a little bit like this so that they can collide to really
Yeah.
make it an S matrix.
Yeah, yeah. So exactly. So this is an S matrix in quote, but for what I will discuss, it's okay to stay in quote. It's just going to be an analogy, but it's going to have even the thing out before the limit will have the right properties to have the right properties.
Sorry, but isn't that true as Shiraz showed that if you have this sheet that there is no collision in the bulk? So in order to have the S matrix interpretation, you would have to be on a little bit on this side, right?
Yeah.
On the timeline
Yeah.
separated side.
Yeah. So this, yes. Yeah. So we'll come to that later, Shiraz. So at the moment, this is not a very good scattering experiment because if you actually look dynamically, what happens if you hit with a hammer at a point 0 here, it will go through all sort of geodesic through the bulk, and so it's not yet localized in the transverse plane.
Yeah, there's no bulk point singularity.
There's no bulk point singularity yet. But still, let's call it some amplitude. And so if you think about this language, this is like the matrix element of like 1 plus I times the connected part of the amplitude. You could write it like this. The 1 is important. There's a chance that nothing happens, contribute to that. The next one here, the anti-time order conjugate, the second guy, give 1 minus I m star. So there's a matrix element of that, matrix element of that. And the last one is just the matrix element of 1, the identity. Okay. And there's a 4 for the ring, which is also 1. Okay. So one of the things that is going to play a very important role in just in the interest of time and to avoid repetition, I will not do it today, but I will just say it in words, is that when we think about this S matrix causality constraint, the whole game starts from reconstructing the amplitude from its imaginary part using Kramer's Crony type dispersion relation. So you want to use the imaginary part of the amplitude is something that plays a very important role in this causality constraint. So here I'm just going to define it and see that on the CFT it also has nice properties. Okay? So if you wanted to define something like the imaginary part of the amplitude, again in quote, well, you manipulate the time order and anti-time order guy. So if you add those, you will get m minus m star. But you still have to the 1. So you have to add these and subtract the 1 twice, which is exactly taking the expectation value of a commutator. Commute 1 and 4, and commute 2 and 3. And
you will say, right, why this particular thing should be thought by the scattering in
yeah.
the bulk of something. So this is to be in the bulk.
Yeah, yeah, that will come later, but yet it's not yet localized.
Okay.
But let me see that it has nice properties, and let's see that it's an intrinsically interesting object from the CFT. Okay. So one thing that is nice about it, first of all, is that when you work out its OP in the 1-2 channel, in the 1-4 channel, let's call it rho 1-4. It's the rho coordinate from that singles out this channel. So rho 1-4 go to 0 is the thing. You get the thing I wrote before. Rho bar 1-4 times some coefficient, which are positive, c square. And what the commutator does is that when you study the expansion around, like if the points were space-like, so let me draw the picture a little bit smaller. So if I have points like this, 1, 4, 2, 3, like the idea is that if the distance is space-like, you get power of x14 squared to something. When this becomes time-like, this becomes minus, you need to put the I epsilon. So it becomes the absolute value to x power I pi time the thing. So you get exactly the same thing when you continue this OP term by term. And so when you do one continuation, you get x power I pi times the exponent. And when you compute the commutator, you need to take the difference between the two possible continuations, which gives you a sign factor. So this object here is as an OP that is written by, is proportional to 2 sine square of specifically pi times delta minus j over 2 of the operator that is exchanged. It's a 2
square because
sine square because there's a commutator on both sides. Yeah, and here I'm taking the operators to be identical for simplicity.
I missed this thing for the face. Could you say it again, please?
Yes. Yeah. A term in the OP will have, in Euclidean OP, you will have f14 square to some power delta minus something. And in order to understand the OP, you can weak rotate the OP as we discussed before. But in Lorentzian signature, this x14 square, the I epsilon will be important. And the I epsilon tells you whether you are the operator ordering of these guys. So if you want to know the Weidmann function, so O1, O4 will give you something like, when it's time-like separated, you get a phase x of I pi something. But if you want the operator ordering, you will get the same thing with the other phase. So each power log, which was real Euclidean signature, acquires a phase, and the sign of the phase depends on the operator ordering. So when you take the commutator, you get a sign factor from this commutator, and you get a sign factor from the other commutator.
It's which sheet you're on, yes.
Exactly, which sheet you're on. Exactly. So maybe in the x square plane, you have a branch cut on the left, and here you have, say, the time order, and here you have the anti-time order below. So the difference between them is a sign factor. Thanks. Yeah, drawing it was better than what I said.
Delta minus j you wrote, not plus j is the same, I guess. Yeah.
It's the same, exactly. Delta, because j is an integer, is all the same. Yeah. Okay. Great. So this is the expectation of this commutator. I think you need a half, maybe minus half or something for, but yeah, you get this thing. This has a nice interpretation. So actually, the thing without the 2 sine square would be exactly this thing. This OP is the OP representation of the boring quantity. This is like the one part of the S matrix is that. And then what I'm saying is that when you compute the commutator, you multiply that boring part by 2 sine square. Each term gets multiplied by 2 sine square. And then the important property of 2 sine square is that it's positive and bounded. Okay? So immediately it tells you that this quantity here, but it was already is bounded even if you don't take commutators, but somehow taking this commutator make it positive and bounded. Okay, so that's nice. So term by term it's bounded, and therefore the whole sum is bounded by.
So in particular, it's smaller than the boring quantity.
Yeah.
Because everything was positive to start with, and now we are multiplying term by term with a positive number.
Exactly. It's important that this is positive. This is a sum of positive terms.
Sorry, I didn't see these boring quantity here. Boring quantity I have to do with 1, 2, right?
Yeah, so if you apply this, if you take this configuration that has the, let's see, how does that work? The simple argument is that if you take this 1, 4 here and given operator ordering, you get a phase. And if I apply the other operator ordering for 2, 3, the phase will cancel. So the sum operator ring where there are some orderings where the phases add, and some orderings where they cancel, and the boring one, this boring one is the case where they add. The phase cancels.
Abhijit, I was thinking of this as 1, 2, and then the various operators being exchanged in the normal OP.
So that's not what it is. It's a 1, 4 OP.
Is it 1, 4, but 1, 2 are brought together, and then how far it's going is the 1, 4. 1, 2 are very near to each other.
Yeah.
So it's going from 1 to 4. 1 and 2 to 3 and 4.
Yeah. So
yeah, but But here the sign factors are multiplying in the 1,4 OP, right?
Exactly. So this is a complicated representation of 1.
The cross channel.
Yeah. In the cross channel, it should be just 1, but in that channel, it's a complicated sum.
I see.
But it's a sum of positive numbers. Yeah. Okay. So that's the first properties of this thing. It's positive and bounded, so we can control it. And eventually, we're going to make integrals of this thing. So knowing that it's bounded is very important. The other thing that is nice is the following: is that
It's literally of 1 or also the deviations away from 1? I mean, the boring thing is...
no, yeah, it's 1 plus dot dot dot,
Yeah.
and this really includes a dot dot dot. Yeah. So yeah, and maybe I should mention here, I wrote it improperly. Is the dimension of the external guy minus the dimension of the internal guy. Okay? That is actually plays an important role because of the following reason. So if you take a theory that is either a large n, that has either a large n expansion or weak coupling, so somehow your CFT is weak coupled, maybe n equals 4 with a small tail of coupling or something like this, then the scaling dimension of the things you can exchange in the O1, O2, OPE, it contains operators that are these so-called double twist families, which are n and j, which are basically O1 and O2 with a bunch of derivatives between them. And derivative can have angular momentum and powers of d square. And the anomalous dimension of these guys is the sum of the parts plus j plus 2n, number of Laplacians you put, plus some order 1 over n correction. And this combination is exactly the thing which is killed by 2 sine square.
Including derivatives thereof.
Including derivative thereof, yeah. So it's exactly, so 2 sine square is order, so it's square, so you get the suppression twice, which in the 1 over n expansion, okay, it depends whether you call n square, and then for matrices to be this, it's basically order of genus 1 in the 1. So it's basically is order 1 loop in the in genus expansion, 1 loop in large n. So if you look at the connected correlator with the sphere topology in the large n expansion, this does not contribute. It only contributes to like a torus topology or some kind of loops in the bulk of AdS. Okay, so this is very small. So that means that the OPE, this object, this commutator square, is saturated by single traces. So the OP has single trace, double trace, triple trace, and so on. This commutator kills a double trace.
The OP coefficients could also scale as one, right? Especially for the single data.
Yes, how does it work? Yeah, so they are scaling of 1 over n in both the coefficients and yeah.
So you're saying even for double trace operators, the OP coefficients are 1 by n?
Now, yeah, so the double trace OP coefficients naively start at order 1 because it's like a naive Taylor expansion. So naively they start at order 1. And the important thing is that, like, why do we get this commutator vanishing? Is because, like, if the OP was just like a Taylor expansion, you would just get integer power. Right? You just get x1, 2 squared to some integer power, right? X to some integer power. If the OP was literally a Taylor expansion, you just get integer power, and the commutator will vanish. So the thing that makes it non-vanishing is the anomalous dimensions. Yeah, this is an exact statement at any lambda. At any lambda. Yeah, deltas could get corrected, but delta minus delta 1 minus delta 2 will be order 1 over n. So this can be a function of lambda but the scaling with n is universal. So this is true even at strong coupling holographic theories. Oh, sorry, there was no.
So this formula delta of lambda would be delta 1 of lambda plus delta 2 of lambda.
Exactly.
Okay.
Exactly.
Simon, I'm just asking Abhijit's question again. Suppose we look at the Taylor expansion part. There the OP coefficients are n square larger than square of OP coefficients for single trace exchange. Because single trace exchange OP coefficients are 1 by n, whereas the Taylor expansion is just 1. And so you get 1 by n squared, 1 by n times 1 by n for single trace exchange, but just 1 here. And so in that case, won't the fact that the anomalous dimensions are 1 by n squared, won't that precisely contribute? Or are the anomalous dimensions 1 by n squared and then that's squared? Is that?
Yeah.
It's 1 by n.
Yeah.
Into the 4, yeah.
Yeah, exactly. So you get small times small from the square. Yeah. Yeah. If you only had one commutator, it would contribute with the sphere topology. All right. So this object is interesting. Like, so if you're going to study, for example, a theory that has a large n expansion, this object is very nice because it only has single traces in it. Okay.
So, Simon, can I swap 1, 3, which I can, I guess, right? Because they are space-like separated.
Yes.
Then I get a crossing equation for this quantity.
Yeah. Yeah. And now exactly. So now this is my next topic. So how do you try to? So one thing you can ask is, can we get like constraints on this double commutator square without having to relate it to the original thing? Okay. So this trick goes in the name of dispersive sum rules. And okay, I mean I could keep going forever, but maybe I can aim to wrap up in like half an hour or so.
Yeah, half an hour is okay.
Okay.
We're very relaxed.
Awesome. Okay, so okay, I will just try to give some intuition. We'll discuss hopefully next time more, but let's just get intuition from S matrix again. In this context, a basic game you can play, I'm going to just assume here the usual S matrix axiom, that you have analyticity in the Mandelstam S plane.
So
in the
can I
F plane.
ask one more question that I
Great.
wanted to clarify?
Yeah.
So in what sense an S matrix is sine squared times 1? Is it a familiar fact?
Yeah. Yeah, I would write it down in 2 minutes.
Okay.
Great. Yeah, this. Yeah, we'll write down the analog of this in flat space, and you will see the point. Yeah. Okay. So I'm going to explain the basic manipulation you will get in flat space in order to get constraints on the imaginary part of an amplitude. And the thing you will do is you will try to draw some. Okay, imagine you have some branch cut, and okay, we're gonna have in mind some kind of separation of scale with a zero scale and a light scale, and we're going to do some contour integral that look like that. And there's going to be some mass scale here that is heavy. Okay? And we're going to go around here and do something like this. Okay? And the idea is that we want to write 0. I'm going to put thing in quote. It's not yet fully precise, but just to get a sketch of the thing, we're going to have to put some inverse power of S that's large enough that MST, I'm going to put K plus 1 here, MST at fixed T. Can do this. And at infinity, on this contour C, would give 0. So C is the union of these two branches. And if this power of S is large enough, such that this amplitude is bounded and decays, you can deform the contour and get 0. Okay? Because the amplitude is analytic in the upper half plane. So what does it give us? This tells us that minus the integral over the arc is equal to some integral from, say, m squared to infinity of ds over sk plus 1 of the discontinuity, which is the imaginary part of m. So you get some rules like this. So it relates. So what does it do? Usually, the way we would use this type of sum rules is that it gives us it relates this imaginary part at high energies. This is the high energy processes in terms of something that you could imagine computing in a low energy EFT. So this gives some kind of relations between physics at low energy and physics at high energy. Okay? So causality through analyticity. So analyticity give you these relations. And somehow this is encoding causality. So we have these relations. And your question was, okay, how do you get this 2 sine square factor and so on in this framework? What we do then is that
and you have to deform both up as well as down.
Absolutely, exactly. And with just the correct relative coefficient that you get the imaginary part here. So why is it useful to get the imaginary part from an S matrix context? It's because, so what do we know about this? Well, we know nothing. Like, for example, in quantum gravity, we know nothing. About the Planck scale, what the hell is going on here? We know nothing. But we still know some kinematics. If we assume that the amplitude preserve Lorentz invariance and actually just rotational invariance in center of mass, we can still write like a partial wave expansion of this. So we can use, so for this part, we use partial waves. And that gives you a formula for the amplitude. And let's say that T is small enough that we're in a physical region. You get a sum over spin of some coefficient, Aj of S, times say some Levin polynomial of 1 minus 1 plus 2t over S, something like this. So you get some, this is like the scattering angle. Okay? And T is negative, so this is between -1 and 1. Okay? So when you use this partial wave expansion, use it at high energies because we know literally nothing, so at least this allows us to parameterize our endurance. Can I calculate what happens? What is nice about the imaginary part of M, so is that this turns into the imaginary part of A. And we actually know something about the imaginary part of A. And the reason we know something about the imaginary part of A is that in principle, how we know is that Sj is 1 plus I Aj. In principle, all we know is that this is less than 1. So the S matrix projected into a partial wave has to be, right, is a matrix element of a unitary operator. It's a complex number less than 1. Right, so this is basically, because you have a normalized 2-particle state. You take the expectation value of a unitary operator in that. It has to give you something less than 1. And what it gives is 1 plus I times the amplitude in this partial. This A is what we normally, this is the connected amplitude. So it is a 1 there. So if you take this formula, so Aj is a complex number. But this relation tells you basically that the imaginary part of Aj, well, if you write Aj as a phase, x bar by theta times Aj, I want to say that the imaginary part of, sorry, this is not the right way to do it. Sorry, this is not the right way to do it. I want to say that, let's say that S is some S, which is 1 plus I Aj. Let's say that this is some norm times some phase times Sj. You can say this. Like if it's an elastic process, you will have less than 1. If it's elastic, this norm will be 1. So if you take imaginary part of Aj, that's like the real part of S minus 1. Something like this. I think I'm screwing up. I was trying to get 2 sine square from this math. I think I said it wrong.
By Martins, you mean really mod or with this JJ?
Can you say it again?
You're taking really mod of this 1 plus IAJ or this
Yeah. So this is the correct statement. And this I'm not sure is the correct parameterization. That is the correct true statement of unitarity. I'm trying to write this in terms of 2 sine square.
Of that angle.
Yeah, but I think I probably have not used the correct parameterization.
I thought the only condition that you get is this: the imaginary part is positive. That's it, right?
No, it's between 0 and 2.
The 0 and 2, yeah.
Okay, so you do see the parallel. Okay, maybe okay.
Oh, because that
This is the 2 sine square is not completely clear, but you see the parallel at least. Yeah. Okay. Yeah.
So in some parameterization of theta, this.
Yeah. With some appropriate parameterization, this becomes this maps. Okay. But yeah, the important thing is that this satisfies this exact same inequality as a 2 sine square factor, and what we get here is so basically this thing here is the imaginary part of M is the sum of imaginary part of AJ.
Sorry, and 1
and
is
this
like
is
AJ equal
bounded.
to 1.
Yeah. When is AJ is equal to 1 is then is when you have complete absorption. But imaginary part, yeah, this normalization it looks a bit weird, but imaginary part of AJ is equal to 1 is what you get when S is equal to 0. So if you have a complete absorption, this is 1. So it somehow makes sense. Okay. So it's also like if you think about 2 sine square, it's between 0 and 2, but if it oscillates an average, the average is 1. So it's kind of a natural normalization. Okay. But okay, you can debate.
So let me ask a very stupid
Yeah.
question. This imaginary part of AJ is greater than, is that assuming AJ is small?
No, this is exact. This is exact. Just because it's a matrix element and 2 to 2 states.
Yeah. So suppose I say AJ is x plus iy.
Yeah.
So I get
Yeah.
1 minus y.
Yeah. So you get a stronger statement. Yeah. So in general, yeah. Let's work out the complete general statement. Exactly. So let's say that AJ is equal to x plus iy, and 1 plus ij is equal to 1 minus y plus ix. And then the statement is that 1 minus y square plus x square is less than 1.
Good.
Which tells you something about, so if you have if x is not 0, yeah, exactly. Yeah, okay, yeah. So if you're on the origin, it's here, the projection of this is going from 0 to 2. But if you know that you are not on the real axis, then you get a smaller range. So the full statement of unitarity is stronger than that.
It's stronger, but that is true. Yes.
But that is true,
I see.
unconditionally. Yeah. And part of the game here of what we do in this constraint is we're actually just using that. In fact, just using the positivity, we're going to learn a lot of things.
Yeah. So you're saying that suppose that was not the case, then that there would be sum of something larger than 1 plus something positive.
Yeah.
So it could be possible.
Yeah. Yeah. Great. All right. So
usually we just work with that to one side, I think, right? It's greater than 0 because we are perturbating.
yeah, exactly. So in this S matrix bootstrap constraint, we actually use this in 2 ways. So in the actual calculation, we only use positivity, but in order to show that this integral converge, we need to use this once. And using this, we can show that this integral converge for k greater than 1, but we'll discuss this longer, more at length. But yeah, we need this statement to know when this integral converge. Yeah. And so I just want to have an analogy here. So what we get from this is sum over every states. So what you get in this sum rule here, on the right-hand side of this sum rule, we get integral over s greater than some cutoff, ds over s k plus 1, times some number that is between 0 and 2, times some Legendre polynomial. Okay? And what I want to explain now is that when you manipulate the orbital product expansion, the 2 sine square will become that factor. And then the conformal block will somehow become this Legendre polynomial. So there will be a limit of the crossing equation where the CFT crossing equation looks exactly like that. And this integral here will become the sum over states above some cutoff delta gap, and so on. Okay, maybe delta 0.
So the left-hand side is that EFT, right? The left-hand side of
Yeah.
this is EFT.
Yeah, exactly. So there'll be left-hand side that we can calculate on EFT, and the right-hand side, that's a sum over AVO parameters.
So, and here you're going to, imaginary part you said was positive. What
Yeah.
about that P thing?
This is a Legend polynomial.
And that is evaluated at some argument where it's also positive?
No.
No, okay.
Yeah, this cos theta is, yeah, Pj is an oscillator function, it's not positive. So in order to actually learn something from this equation, we'll have to manipulate this further.
Analytically continue T or something like that to go to a place where this is positive.
Yeah, but then it doesn't converge.
Okay.
So we're not going to do that. On the other hand, it turns out that these Legend polynomials are oscillatory, but when you integrate it against wave packets, you can make every one of them positive.
I see.
It's just like kind of Fourier transform for impact parameter to Fourier. So there's a conjugate space where things are positive.
I see. So worded in terms of T, you've got no useful statement there.
No, exactly, yeah. So in order to get something useful, we'll have to manipulate this a bit. But still, that will be our starting point.
For physical values of T, it is possible, though, right?
No, Pj, no, when T is less than 0 and S greater than 0, this is oscillatory and not positive. It's like a cosine.
But when this argument is greater than 1,
Yeah, you could, yeah, exactly. But the problem is that when we apply this for things like massless particle that have a graviton exchange and so on, you cannot go to T positive. So the sum does not converge. Exactly, yeah. So, yeah. This is one a very important point in this business is that we're going to try to get inequalities about what can we get on the left-hand side knowing that this is positive. And we actually only learned something, like, and the idea is like a sum of positive numbers is positive, duh. If it converge. Right? No, remember, right, 1 plus 2 plus 3 plus dot dot dot. What's the sign of that? Okay, right, it's very famously minus 112, right? So you know, like, it's not sufficient to just manipulate things and say, oh, it's a sum of positive numbers. You really have to know that the sum converge.
And you're saying we know that it converges when T is negative because that's like a physical scattering experiment.
Yeah, and we have to further integrate T against a normalizable wave packet, and then this argument works. Yeah. So the precise statement is that when this is integrated against a normalizable wave packet, this converge for K greater than 1.
So even without integrating against a wave packet, if T is negative, so that it's like
Then it doesn't have to converge.
that doesn't converge.
No, not absolutely necessary. No.
Isn't that just convergence of the partial wave expansion for the S matrix?
Yeah, but the integral over S is not clear that it converge.
Okay.
Because you have to control, like roughly speaking, as you increase the energy of the scattering experiment, your target could effectively get bigger and bigger, your cross section get bigger and bigger. So you have to control how your target grows with energy. So yeah, controlling both the sum over spin and integral over S really requires these wave packets. Unless you're Martin and can prove the Forster-Martin bound, but like this is like way harder than what we're going to do.
I see. So you're saying for any given S it converges, that sum converges.
Exactly.
But then the integral may not converge.
Yeah.
After on the imaginary axis.
Yeah.
on
On the real axis, we just need to integrate on. Well, we need the whole arc to be 0. Yeah,
Yeah.
we need the whole arc. We need to control the whole arc.
Yeah. But so say we know something about the behavior at very large S.
Yeah.
For what T?
For fixed T, yeah.
For fixed T.
Yeah, if you knew that, you could use it, yeah. But one of the points we'll discuss tomorrow is that you don't need that.
I see.
Oh.
You know, the wave packets sound like a nuisance, but actually the wave packets make the story nicer. You get stronger results using the wave packets than using
So it's
fixed
more
T.
physical.
So wave packets are good for you.
So you don't need to know a priori there is some sort of a bounded behavior at infinity. I mean, you need some input, right? Some physical input.
Yeah.
Controlling that.
Yeah. So okay. Yeah. This is maybe I can say it. It's fine. So the physical input really is that so causality gives you an elasticity and some notion of boundedness. Because if you have a function that grows exponentially in upper half plane, it's not causal. Like a Gaussian is not causal, right? So causality gives you some notion of boundedness, which is a bit weak. But when you combine it with boundedness on the real axis, you get boundedness everywhere by some kind of maximum principle.
But why not use the chaos bound or the
Well, that's
bound?
but this type of arguments are a way of deriving the chaos bound in this context. Okay. So the chaos bound applies rigorously to these wave packet amplitudes. Yeah, these arguments are a way to derive that. Basically, because you can write, they allow you to write, say, the derivative of the amplitude as you go in this direction as an integral over positive quantities that are positive by this argument, and that, yeah, so you can derive the chaos bound from this.
I see.
Yeah.
And in spirit, that is mimicking this Martensen-Stanford-Schenker.
Yeah.
But then not at fixed t, but at fixed impact parameter.
Yeah, exactly. You need a wave packet that localized to small impact parameter, or fixed. Yeah. Yeah, great. Okay, so let's sketch how we do this from the CFT viewpoint. It turns out, okay, I didn't give references, but okay, a lot of this discussion here is in the paper with called AdS bulk locality from sharp CFT bounds. With Simons Duffin, Leonardo Rastelli, and Dalibel Madzak. About the previous paper classifying the sum rules. The idea there is that...
Sorry, so there's a derivation of the chaos bound is also in there from this type of arguments?
that was in my earlier paper on the Lorentzian inversion formula.
Oh, that was there, okay.
Yeah, exactly. Yeah. So if you look up, there's this kind of introductory section there, we explain how you get the bound and chaos from dispersion relations.
And that was bounded chaos in AdS space.
Yeah.
And is there a derivation of this, S, no more than S squared at fixed t in flat space from similar?
Yeah. Yes, I think so. For when you have wave packets, I think so. Yeah.
Okay.
So I think it's yeah. Great. So what we're going to do is that we're going to have the same kinematics here with two spectators. And now we're going to take this statement about vanishing commutators to its extreme. We're going to integrate two things on the like sheet. Let's call it x1 and x2. And we integrate them on the like rays.
Sorry, are we in AdS or flat space now?
This is a flat space. This is a CFT. So this is a CFT calculation. I study a 4-point function. And before, I was looking at this rigid limit here that somehow had to do with scattering. But now I'm going to do something slightly different. I'm going to integrate over 2 points on this null sheet. Okay? And the basic idea is the following. Is that, okay, I do something like integral dx minus of phi x1. And the basic idea is that these things should commute. Because they're on the same like sheet, so the distance between this point and this point is always space-like.
Because it's 0 squared plus 1
Yeah,
squared.
exactly. So this should be 0. And there's a little caveat. This should be 0 if the integral converge and makes sense. If it converges. And we have to come back to that. But basically, this is naively 0. Because everywhere inside the integral, if you can commute the commutator at the integral, it's clearly 0 because it's always space-like. Okay? And then we sandwich this in the state 1, 4. 4, 1.
And you didn't
And
use the
this
fact
should be
that
2
the
and
other
2.
guy is also space-like with the other guy?
It plays no role. No.
1 and 2.
Yeah, and I could put 1 and 4 here and the other. Yeah, it's going to be in the calculation. For the actual calculation, we'll take them to be space-like. But for the statement, it does not matter.
When this guy goes here, right, so that it's time-like, because
yeah.
previously they were like that.
Yeah. Yeah, but there was no. Yeah. No, it's not. So it's effectively there's going to be 3 corners. So there's going to be some corner of this integral where x1 and x2 both go to infinity. That's like the boring part. Then there's be one where this guy goes here and this guy goes here. Then this maps to the absolute we had before. And then there'll be the reverse of it. Yeah, so the picture will always look like what we had before or permutations of it. Okay.
Just to make sure x2 and x3 are separated in the transformation.
Yeah, exactly. So there's an expert between them. Great. So we take this sum rule, and so we take this matrix element and we try to make sense of it. And the thing we get is, okay, we expand it in two forms. And now there's a very nice lemma. So again, to Simon Duffin and Krafchuk, that the integral of dx minus of a field acting in a vacuum gives 0. And this we can understand physically. It's because this is basically taking a field with momentum 0. So this would be creating a state with momentum, one of the Lycone energy equal to 0. But if the Lycone energy is equal to 0 and all the states have time-like Lycone energy, there's no state with this property. So this has to kill the vacuum. Okay. And you can also show this using some kind of I epsilon calculation. So whenever you calculate, if you think about the complex x minus plane in a correlation function, all of the singularities will be in the lower half plane. And then if the integral converge, you can deform it, and you get 0. So
this is not like this soft mode, changing the vacuum sector and things like that.
yeah, in order to make sure that doesn't happen, we need to think about convergence. Yeah. In principle, this could give some funny delta function at 0 momentum, soft mode, blah, blah. But we'll avoid that momentarily. But let's just proceed naively. Let's assume this converge. So if you take one of the term, you get 4 times integral phi 1 acting in the vacuum. I said that integral phi annihilates the vacuum. So this quantity, which was 0, is equal to the expectation value of a commutator going this way. And the same thing on the left, I can replace this product by commutator. And okay, this was 2 and 3. And there's going to be another term, which is minus 2 and 3 Schwatt. So you see how I turn. So what did they do, right? So we started with some statement about this equals 0, and then we integrated it in such a way that it turned into expectation value of commutator square in a different channel. Okay? Well, that is nice because now it gives a relation intrinsically on this double commutator.
Sorry, I thought we were getting that kind of an equation or double commutator even without integration. Maybe I'm wrong.
Now, yeah, without the integration, this will not kill the vacuum, so you don't get that. Only that is 0. So it's important to integrate.
So it wasn't, I mean, all that you needed was that it inherited the vacuum, right?
Yeah.
So this is a special case of that, when you integrate
Yeah.
on type space, but
Yeah.
there could be more general things.
Yeah. Yeah. And maybe I can also make another important analogy with the S-metric case. So notice that there's 2 terms in this process. So let me put numbers here. And let me put 1 here and 4 here again. That's my favorite position. So there's a term that is a scattering of 1 and 2. Sorry, I have too many 1s. Let's call this 2 and 3. Okay. So there's a 1, 2, 3, and 4. Okay. So there's one term where say 2 goes to the past. So there's going to be a term that is like absolute for 1, 2 going to 3, 4. Okay. And in the S matrix case, you know that crossing symmetry, it was important to use the full upper half plane here, right? Before I talk about the contribution from the cut on the right, but there's also a contribution from the left. And contribution from the left involves the complex conjugate of the amplitude for 1 3 bar going to 2 bar 4. There's a cross amplitude here. And in exactly the same fashion, here we get two contributions that are related to two different processes. So the process where I put one here, followed by 3 here and 2 here, that process will map to 1 3 goes to 2 4 amplitude. And it's complex conjugate because there's a bit of a different operator ordering than the other ones. So when you interpret this, you can very precisely interpret this in terms of this as an analogy to that. Okay. So we get this type of relation.
This integral, this quantity is from how many cross ratios do we have? In how many parameters?
Ah, great. Yeah, so in general, you think of this as a function of x perp, and there's one transverse cross ratio. So this, we call this the B sum rule. It's B of V, where V is a cross ratio in the transverse direction. Yeah. So it's a function of one cross ratio. And call it BK, and the K I have to explain now what it means. And it will map to the power of S, the K that we had a minute ago. There's an issue here, is that if we think about convergence, all we knew before is that, so this limit where x2 and x3 go to infinity is the limit of large boost. And all we knew before is that the correlator was bounded at large boost. You see, we know that this thing is less than a constant as x minus go to infinity. So if we integrate dx, if we do a double integral of a constant, it blows up. Okay, so this diverges. Okay, so we have to be a little bit, we just have to fix this problem. Okay, so there's actually one nice solution. One solution is that, well, not solution, maybe a variant. If the field phi was not a scalar field, but was something like the stress tensor, replace phi by integral dx minus t minus minus. Then under boost, this rescale in a way that makes it get smaller. And this was diverging quadratically, but here, each of these minus index improved 1 power. So if you have two stress tensor, this would converge quadratically.
So you say it's less than equal to a constant because it was less than equal to that simple channel,
Yeah.
which was a constant.
Yeah.
Okay.
Yeah. So when you do integral of stress tensor, it converges. And in general, if you took an operator with J1 indices and J2 indices, it would converge provided J1 plus J2 is minus 1 is bigger than 1. So J1 plus J2 is to be strictly bigger than 2. Okay, so if you put enough spin on the thing, on the operators, spin helps. Spin is great. Okay? This is part of why these things would be more constraining for gravitons than for scalars. Okay? The other solution is to put something in the denominator. Just add by n some denominator.
You mean the x minus integrals?
Yeah, inside that integral. So suppose I add some power of x13 squared here. Suppose I manually add something like this. And same, I can put some factors here. x24 square, Suppose I put some power downstairs, like this. then with these powers, the integral will converge. Because this thing vanished to infinity. And that works. And actually, playing with these powers give us something that helps us get something out. There was another issue with this commutator here is that actually by symmetry, if the fields are identical, we get 0. So the identity was a little bit like 0 equals 0. So if we multiply this by something that is odd, it actually becomes interesting. So we're going to put some x squared here. I forgot what it is, but yeah, x squared minus something like this. But if you put the correct numerator and denominator that we explained in the paper, then this is a valid sum rule that gives something that is non-zero. Okay, and then you can put more powers, like r powers of k if you want, and it gets better and better. Okay, or k over 2, or there's some map between these and the things you can get. Okay. So these are some rules. One thing I can say is that now it looks like.
So intuitively, the reason at the beginning we were interested in fixed insertions, but because could I say the following, that if I'm integrating, I'm going to get contributions that are anyway dominated by what happens at infinity. So it's sort of like taking them fixed and very far. Is that why this is more or less the same physics as?
Yes. Yeah, there will be a very important contribution to the integral from this rigid limit.
Okay.
Yeah.
That will be the dominant one.
Yeah, and this is dominant. Actually, what happens when you put an operators with large delta? What happens is that when you do the OP between 3 and 4, the OP tends to repel at large delta, so they'll be dominated by the terms that are as far as possible from each other. So putting large delta in the OP will really force you to the rigid corner.
Simon, this expansion converges for both channels at some parameter v.
Yeah.
And there is some basis that we know that it expands in and so on, some integral of conformal blocks.
Yeah, exactly. So I will describe that in a minute. So I'm almost, I guess I would try to wrap up. So the key property of these sum rules is that, remember there was this sine square factor. So when you plotted the sum rule as a function of delta and before, there was a place delta 1 plus delta 2, delta 1 plus delta 2 plus 2, and so on. All the sum rules are these double zeros from the sine square factor. Now, what happens when you put this denominator is that you get the thing that used to be a polynomial now is no longer a polynomial, so the commutator is no longer 0. You get some kind of delta function contribution on this arbitrary. So basically this cancels, so you get something like x, you get things like this, where you cancel the first few double zeros. Okay? So k equal 2, this guy it cancels the double zero on leading trajectory. Okay? And if you put more powers, it will cancel the double zero in the two leading trajectories and so on. So it cancels some of the zeros that you add. And it's precisely because you're canceling some of the zeros that you get convergence. Okay?
So by cancelling zeros, you mean that those double trace operators will be visible?
Yeah, exactly. So you become sensitive. So this sum rule here is sensitive to the leading double trace family.
And this is the statement that for scalar exchange there are some contact terms that goes less than equal to s squared.
Yeah. To leading. Oh, they call double twist in this context, but double trace in large M. So this sensitive, the subtraction adds sensitivity to the leading double twist. Okay, but that's how it does.
And the fact that you didn't need any subtraction for gravity is the statement that there's nothing, no contact with gravity that is less than equal to s squared.
Yeah, in some channels at least, but yeah, it's not such a straightforward map because by taking this integral of t minus minus, you only constrain so many elicities. You don't constrain all the elicities. The one-to-one map between the statements is not image yet. Okay. Okay. So, okay. So I will skip.
If I want to compute this, can I just naively compute the 4-point function and then do the integral? Is that the same as the?
Yeah. Exactly. When k is large enough that it converge, you can swap everything. Yeah. Great. Okay. So, okay, probably 15-ish minutes I can wrap up. Great. Okay.
And once you add these denominators, is it still true that the integral acting on the vacuum vanishes?
No, exactly. It doesn't vanish. But the only thing that the only non-vanishing part is due to this double twist contribution. Exactly. So in terms of algebra, it looks weird, but when you actually evaluate it on blocks, it's a very simple statement. Yeah, thanks. Okay. So the last thing we need is to localize to a bulk point. To a bulk point. Right, because the physics that we're actually probing here, as I drew again, is that somehow we're sending something here, and we have a high energy, so it's localized to a null sheet, but it's exploring all null geodesics on this null sheet, and there's an infinite number of null geodesics that go from 0 to pi. So this is not yet localized in the transverse space. So in order to, actually the thing that would be nice is instead of fixing the impact parameter B, there's a quantum number that is actually has a nice interpretation, which is to fix the transverse momentum. So you can try to have a process that has a large momentum transfer in AdS. Okay? So let's try to understand what this is. And the nice thing about empty AdS is that you can guess what the right answer is based on group theory. In principle, you could put wave packets and just see that it localizes, but the group theory guides you here to do it nicely. Like everything I'm going to say you could do using dumb Gaussian wave packets, but then you wouldn't be able to calculate things explicitly. But with the group theory, you can actually calculate. So the picture is the following. So this is AdS d plus 1. And the physics is going to localize on this null sheet, which is a hyperbolic space in d minus 1. So the impact parameter space lives in AdS, in H d minus 1.
Wait, sorry, help me understand what the boundary on the cylinder now. Where are your boundary null things and where are your fixed points?
Yeah. So there's 2 points at pi, 2 point here, but I'm slightly and not in the bulk point kinematics. I'm still in the Regge kinematics on the Regge sheet.
And the sheet is going.
Yeah. So we have a null sheet. Yeah.
Okay. Okay. On the boundary.
Yeah. Exactly. So if I add a cylinder. So I take a saber and I slice it like this, and then I slice it the other way. They intersect on the codimension 2 line, which is this H d minus 1. Great. So the momentum, basically p perp square, the idea is that p perp square is a Laplacian on H d minus 1. So that's a very natural notion of a transverse momentum in AdS. So we're just going to take this as a definition. And then using this, the question is, what do we have to do on the external points in order to single out a particular eigenvalue of the Laplacian in the middle? And the answer is actually quite simple, is that at the boundary, okay, this is a little bit strange, but there's a, in terms of the impact parameter space, this.
You had a light sheet on the boundary which just extends into the boundary.
Yeah. Yeah. Yes. No, exactly. Yeah. So exactly. So because the slice here, the light sheet at the boundary is this arc that goes around.
Yes.
And it's continuously connected to the sheet in the middle.
Light sheet in the
Yeah.
Yeah. Always good dimension.
Yeah. Exactly. And okay. So the claim basically is the following. Is that I mentioned that this is a function of a cross ratio, V, And basically the transverse isometries which fix this thing basically act nicely. You can think of this cross ratio as a cross ratio in the transverse plane. It has to do with this X perp. And that we had, and the picture of the boundary was this thing with the X perp. So effectively, by doing the correct Fourier-like transform with respect to X perp, you can project into something that has a eigenvalue of this Casimir. Okay? And the solution, basically, if you take this BKV, you can define something that we call like B at, which is a function of P perp, which is some integral over dV of bk of v times some eigenfunction of the Casimir, which is some 2f1 that is very explicit, that depends on this p perp quantum number. Okay? So there's a precise, this is basically Fourier analysis on, so the picture is that you have this hd minus 1, and you're trying to do Fourier analysis on this space in terms of the 4 points of the boundary. And projecting into a Casimir in the middle is the same as doing some integral transform on the boundary. So by doing the correct transform, you get to project on the boundary. And
is the spectrum of P perp discrete in any sense? Because this looks like conformal computation.
it's continuous. And actually, this is a V. And this V and this P perp here, you can say that the scaling dimension is D over 2 plus I P perp. So there's a sense in which this is a principal series representation. Yeah. So it's kind of a principal series representation on this thing. Yeah. So great. Yeah. So these are there are some legend polynomials, but continue to non-polynomial principal series.
There's a positivity or something?
No, there's no positivity yet. But I'm going to connect it to the other thing that was not positive, but as a legend polynomial from the S matrix case. Okay. So the interesting regime where we probe a flat space is when this P perp is bigger than 1. This is naturally in AdS units. And we also want to have the scaling dimension of the external, sorry, I shouldn't call this delta A. Delta greater than 1. So what we want to do is that we want to take this functional and act on it with an exchange state and act on it on a block that has a certain dimension and spin in the OP. So you want to act on this with a conformal block. Right, so you want to take this integral and integrate it against a conformal block. So here you get something times some block. And this B itself was an integral over times. Okay.
Where I missed this. What is this conform block? For the external operator?
Yes, let me draw again the picture. So we're doing an OP, say, in that channel. Actually, the nice OP is in this channel. Okay. We're doing an OP in this channel. So we have a scaling dimension delta J that's exchanged. And we want to do this integral term by term in the OP. Because the OP is absolutely convergent, this converge, we can exchange everything, do this integral term by term in the OP,
Right.
and ask what we get. And so the interesting regime is going to be that the momentum is large, and the scaling dimension of the thing we exchange is large, but J is fixed. Okay. And this a priori looks a bit painful, right? Because this is
Like the principal series decomposition of a higher dimensional conformal block into lower dimensional.
It's more like a 6J symbol because this block, this J is inserted in one channel, and then this limit is projecting us to the rigid limit in another channel, and projecting into a transverse Laplacian in that other channel. So it's more like a limit of a 6J symbol. And so this looks a little bit painful, and you see there's a lot of integral, right? There's an integral over dV, which is transverse momentum, and an integral over dx1 plus x1 minus dx2 minus dot dot dot. But the physics of it is that in this regime where the momentum is large, this is highly oscillatory. It's very oscillatory. So this integral is going to have a saddle point. And the claim is that that integral, when you do it, I will just write down the claim, it has a saddle point, and the saddle point is not on the Regge sheet, it's on the bulk point sheet. It's a complex saddle point on the bulk point sheet. And the contribution of the saddle point is exactly, so 1 over, let's call it the quantity I would call mass to the 2k times a Legend polynomial of the spin that's exchanged times 1 minus 2 p perp square over m to 2k. Where big m is basically actually, let's just call it delta 2k. It's basically that. Okay? So we can write it like this. So we reproduce exactly the up to contributions of order. This is exact in p perp. This is for p perp less than delta and delta bigger than 1.
So this is a saddle point in what? V?
It's a saddle point in all 3 variables. All 3 variables. All 3 variables end up, all these 3 variables end up going to a saddle point.
Okay.
And a saddle point is exactly a bulk point kinematics that has a scattering angle of cos theta equal that. Yeah. So this was a bit of a technical issue that people struggled with for some time, which is that in these rigid kinematics, the OP is very nice. It's a sum over 2 sine squared and so on. But if you try to, at this point here, I always do this point like this. If you try to do something that actually looks like scattering, you will want to like rotate this so that this in state and this out state are rotated by some finite angle. And if you do that, you have to cross some extra like sheet, extra like cones. And after you do that, the convergence of the OP is spoiled. And you cannot do anything. But what happened here, the key here was to start with the convergent OP and integrate it the OP converged term by term, and we integrate it against an oscillatory function. And the saddle end up looking like here, but the original integral converged. So we don't have to analyze the...
So basically putting 2 operators in momentum space.
Yeah.
That was the trick too.
Yeah. Exactly. Yeah. So, yeah.
Those are integrated ones.
Yeah. There's a momentum space along like and in the transverse distance.
Yeah. So, okay, so let me summarize. So what this shows is that by manipulating the crossing equation, you get something that really looks like the S-matrix dispersion relation. The important one of the important thing here is that this is going to be useful to control the contribution from operators that have a large dimension. However, we don't need a parametric large n expansion. We just need, the data to be large in some number. If data is more than 20, this is a good approximation. So we don't need parametrically large delta. We just need a numerically large delta. So we'll be able to apply this. So we'll apply to theories with numerically large n and theory of coupling and so on. But we don't need we're not going to need the parametrically large numbers.
So what was the reason that delta was needed to be large to begin with?
Yeah, if it's not large, we made plots of we can actually evaluate this integral exactly and compare with the numerical answer, with the saddle point approximation. So if delta is not large, you don't get a sharp saddle point, and this approximation gets less good.
A priori, why am I taking large delta limit?
Yeah, why do we do this? Okay.
Flat space.
Yes.
Make
Okay.
contact with flat space.
Yes. Okay. Yeah.
But that
No,
goes
yeah.
for massive particles, right? right?
Okay, yeah.
For massless particles,
Yeah.
you do this large energy kind of.
Yeah.
That I thought was a little different
Yeah, okay.
from large delta.
Okay.
Because delta is just the same as the order one
Yeah.
occurrence.
Yeah, so let's discuss what spectral assumptions would be natural. Okay, so the theories we have in mind will look like this. So a function of spin, there's some various delta that contribute, and we're going to be applying to like this is concept of a large gap that people talk about in AdS CFT, but we have a slightly refined version of this, which is that we're going to assume that for spin 0, we can have like any operator you want. Spin 1, any operator you want. Spin 2, you could have any number of KK modes. But we're going to assume that well, there's a unitarity bound that goes like this. But for spin 3, we're going to assume that for higher spin, there's the delta higher spin gap. So there's a gap for the spectrum of higher spin that they're all very heavy and far out there. Okay? Actually, there's a twist that doesn't matter, but yeah. We're going to assume that all of the higher spin guys are there. So with this concept of higher spin gap. So this approximation applies to everything here. On the other end, we still have to treat these guys here exactly without doing the approximation.
But there are these papers where they are, aim to extract flat space physics from CFT,
Yeah.
where the external operator dimension is itself taken to be large.
Yeah.
Where the rationale is something like, you want radius of AdS to be much bigger than
Yeah.
chemical energy.
Yeah. So if you want to study a QFT in AdS, you can do that. And that will be dual to a CFT where you ignore the stress tensor of the CFT. That you can do.
But that's the rationale for
yeah.
flat space limit, right? I thought there was going to be a similar thing that you're going to say for large delta.
No, yeah. So here, what we're trying to do here is to study intrinsically theories in AdS.
Okay.
So, and we care about the gravitons and the stress tensor and all the light modes. But we like to understand how the light modes in AdS can interact, subject to the assumption that there's a large higher spin gap.
No, but if there is no assumption of this kind, then why is this whole thing getting localized at all? So.
Well, these contributions get localized. These do not. But it's still enough to restrict the effect.
So, in the case you have type of high spin holography.
Sorry?
In the case of high spin holography where the high spin diffuse would be light.
Yes.
What would be the qualitative?
Then you cannot use that. Yeah, if you want to study a spectrum that has a lot of higher spin states here, then the sort of EFT logic of separating the heavy and light modes does not apply.
And from the point of view of large AdS, is this some kind of geometrical picture, some interpretation? What would be the difference between the behaviors of locality or non-locality particles?
Yeah. Yeah. Yeah, so there's a few things I can do. Okay, so this was about getting constraints from crossing. But we can step back and ask a question a bit like Abhijit asked, which is, can you do experiments in the bulk that localize to a point, that probe the physics in a point? And actually, I think it's really if and only if you have this tower of higher spin particles, you will not be able to localize to a point in the bulk. Everything you do is like will be smooshed at the AdS scale. So there's no local physics at all then.
At high enough energies, we expect even for massless particles, we expect local physics, right? I mean, the bulk point singularity is very localized.
In holographic theory, in the theory with this property of higher spin gap. Yeah.
But you're saying so far that your external operators also need to be very heavy.
No, my external operators were light.
Oh, just the exchange operator.
Exactly. This is internal. This is internal. The external operators have a mass order 1.
And are you saying that
or 0,
the exchanged operators were light, then because that is not, that the scattering is not very localized in the bulks? So there's no bulk point singularity for that?
No, the contribution from exchange operators that are light is spread out over, give you long range forces in the bulk. Yeah. But these long-range force, you can still probe. Right, you can still fix one impact parameter and another impact parameter and measure the whole force law as a function of the distance in impact parameter space.
But you could have just focused the beams from the beginning so that the whole process happens in a small.
Yeah. What I'm saying is that this focusing will only actually succeed dynamically if you have this
let's
higher
say there
spin
is
property.
such a thing.
Yeah.
Let's say there is such a thing. Then you could do it.
Yeah.
And then because of this picture that everything is happening in the bulk in a small place, even the other stuff would I would imagine would be approximated by flat space scattering, right? Even the other
That
so why is that not?
That is correct. And okay, that was the other part of our paper. So the first part is to show that these AB things are simple.
Okay.
The other part is to show that while the individual like stuff here are ugly, the sum of the like stuff also looks like this arc, this EFT arc that I talked about earlier. So that will also show. So the sum of this like stuff, you can also calculate using a process that's localized in the bulk. And for there, the fact that it's a finite spin that contribute is important. Okay, so that was this dictionary. What else do I want to show? Yeah, I mean, I had a few more comments. So I stress here this particular formalism of doing like these integrals over node arrays and so on. But there's actually, there's some rules that I described, this particular thing here. You can also start from Mellin space and do a contour integral in Mellin space. And if you apply the equivalent integral transform that picks up the analog of the impact parameter, you will land on exactly the same sum rule. Not just approximately, you will land exactly on the same sum rule. So you can use different formalisms and land on this. So let me put it like this. So there's this sum rule that I call B2 of V that was labeled by a cross ratio. It's related to a sum rule B at of P perp. I think it's true for all K through some disharmonic decomposition. It's also related to some integral of something you would call B at of K and a Mellin variable T. And this is equal. And I think it's also equal to something in the momentum space. Some other B at that you can define in momentum space. This has not completely been published in literature, but these are not approximate signs, these are equal signs. So you can really use any formalism you want, and this construction is naturally transposes.
Your boundary observable had one cross ratio.
Yeah.
Now, an S matrix has two things, right? S and T.
Yeah.
How do you do it?
But K is we're taking a moment with respect to 1 over S to the K.
What's it?
We're taking a moment, again, 1 over S to the K.
Oh, I see. So you're matching with one parameter information in the S matrix.
Yeah, exactly. So for example, specifically, if people say that the S matrix, the Mellin space amplitude is analogous, so people have this Mellin amplitude of S and T there. If you do something like integral ds of this Mellin amplitude, and you put S over the first double trace threshold square here and something with U here, if you do this contour integral, you will get exactly this thing I call B at of T. And then if you do if you basically do the Mellin transform of T, you get V.
Which I'm still thinking, the quantity you started with before doing all your transforms on the CFT side had only one variable in it, right?
Well, yeah, but it was secretly this label K, which is how many things I put in the denominator.
I see.
Which maps to how much stuff you put downstairs there.
I see.
Yeah, some programmer there. You can, yeah. There's some natural way of defining it. Yeah, so there's a natural way of defining in Mellin space something which will have double zeros on all except the leading trajectory. And this, basically, if you think about where the double zeros are, you can easily guess which maps to which.
So this K is like power of energy, overall energy?
Yeah.
Okay.
Exactly. So B equal 2 K. So this extracts the coefficients of S to the K in the low energy amplitude, roughly speaking.
So roughly the parameter that we saw earlier was like an angle information.
Yeah.
And
Yeah. Exactly.
So if I take a simple-minded view that this B of V is some sort of correlation which is a function of only one cross ratio and so on, try to do bootstrap with it, would I do that totally wrong? If I just expand the principal series and the coefficients are not positive, I guess.
Yeah, you don't get a lot of constraints. I think you want to combine different Ks and so on. But I think one of the, something that's related to the question you ask is, okay, this basis of functional is motivated by AdS, CFT, blah, blah. But can you use it to do numerical bootstrap of, say, the 3D Ising model or 2D Ising model? And we had tried, I think a whole generation of undergraduate research projects at Mcgill went into trying this. And never quite worked, but 2 years ago, Zichuan Zheng managed to make this sort of analytic functionals actually useful for numerical bootstrap. So I think this deserves to be revisited and extended. But yeah, there's been at least one data point of success. Yeah. They use a slightly different basis, but I think by this logic, I think it should be one more equal sign and related to this other basis.
So let's say I take B of V with some K, then expand in this conformal block from principal series. The coefficients that I get, because those are BK perp, right? Those are not positive.
No. No. No, exactly. You have to manipulate, yeah, especially the, yeah, you have to numerically scan over a linear combination of these things with different T, for example, in order to hope that you get something that's positive for all states.
And then there is
but that's the same for the numerical bootstrap, right? You take some derivative. If you take any individual derivative functional, you don't learn anything. You have to combine them and ask a computer to find positive combinations.
And the crossing equation is that B of V is equal to B of 1 over V, something like that?
No, this B itself has two channels. This already is some information about two channels. And that is equal to 0.
Right,
Yeah.
V itself is
Yeah.
yeah.
It's a particular way of writing 0.
Yeah. And so far we've done, you've taken this dispersion relation in flat space, which didn't have positivity as of now, and reproduced that. Basically.
And reproduce that. But I still haven't done anything useful because, exactly. But then it sets the ground for tomorrow, because tomorrow we'll actually analyze this flat space one, which is much simpler than the CFT one. But because of what I said today, everything we do in flat space will uplift with CFT sum rule. So like we basically defined today, the main result of today is that if you had a valid S matrix sum rule, or S matrix unitarity, it uplifts to a CFT constraints. So we have this uplift map. So the space of S matrix, the space of CFT bootstrap constraint is at least contains all S matrix constraints. It could be bigger, but maybe the Venn diagram is a bit. Yeah. We showed that this Venn diagram like this.
Hopefully it is bigger, right? Because we want.
Yeah.
We expect it.
Yeah. But yeah, we showed a Venn diagram of this type.
But sometimes, at least in this CFT and AdS type literature, one sees this, that for some particular configuration space, it's a bit outside this, but the localization in bulk is such that the exchange diagram vertices are far away from each other, so that you cannot quite associate this interpretation that there's some scattering happening because there's some process that is going on.
Yeah. So this describes these light guys. But more precisely, describe the contribution of these light guys if you don't integrate over these wave packets. So this BV here contains this physics you describe, where you can have a process like in AdS, some particle here that connects with some other particle far out. You can still have a well-defined position for each of those, but they're far.
And then you kind of
and yeah, that.
Take it out somehow.
Yeah, there's a little bit of a. So there's a potential obstruction that these S matrix constraints that are positive at short distance might not be positive at long distance.
Okay.
And in practice, we found that we could always fix it for the ones we used. But yeah, there's a potential. Yeah.
Also, the true flat space limit, where coupling is held fixed, where you go to infinity.
Yeah.
Whenever this can happen, that particle is unstable.
Uh-huh.
In the Lorentzian space.
Yeah.
So if
Yeah.
two particles can scatter into this can scatter into two particles.
Yeah.
And that will not propagate over very long distance.
Yeah, let's see. Yeah, I think this is the most important thing that we wanted to avoid is that, right, people usually phrase this kind of flat space limit of AdS CFT in terms of taking a sequence of theories which have different n's and lambda and taking a limit. And here we really want to just like take a theory that has an n 20 and lambda some number and see what we can say about that theory. We avoid these issues. Yeah, because I don't want to think about the stability issues and so on. Yeah. Yeah.
Yeah, whatever is AdS theory, you just want to focus on a small place. And
Exactly.
See that flat space looks like flat space.
Exactly, and as long as the gap is large enough, you should be able to focus on some region of size that is numerically small compared to the AdS radius, and that's going to be enough for these approximations to be good.
Yeah, but I'm saying that if the coupling is fixed, there will be a length set by that coupling.
Yeah.
After which this thing will not propagate.
Yeah.
Because it decays, right? So at any fixed coupling,
Okay,
you want to take a fixed coupling in the bulk,
Yeah.
you will always be able to take a region that is large enough in units of that coupling. So as long as your AdS is bigger than that,
Yeah.
it will be local.
Yeah, but if we're scattering stable particles, it's a very mild restriction because there's not a lot of time.
What's that?
If we're scattering stable particles, this restriction is not very strong because well, when they localize here, there really is not a lot of time in this process.
Yeah, but obviously it was worried that it would go all across AdS, right?
Yeah.
So that it's not at all like a flat space process.
Yeah, yeah, but this process is when you focus at large distance. I think when you focus at small distance, I mean, okay, there could be a process with a large time delay at small impact
parameters. Choose your
parameters.
kinematics so that never happens.
Yeah.
I think Abhijit is saying that there exist for kinematics in the bulk where it will go 9 over rather than. Are you saying that you choose your bulk boundary kinematics so that it doesn't?
No, I mean, you don't have to. I mean, for example, one thing you could have is you could have these particles create a resonance that decays. And this will just be, you plot the coefficient here and you will see a bump.
No, I'm just following Abhijit's question to ask a more basic thing. The question is that if your process happens over AdS length scale,
Yes,
then it's not a flat space process.
that is correct.
So I'm trying to understand how you avoid that.
Yes.
Okay. Now there exist kinematics for which if your coupling is small compared to size of AdS, this thing will happen over AdS length scale.
Yeah.
So when if you access those kinematics, you're not just looking at flat space physics, right?
Yeah.
So how do you avoid that? That's the question.
Yeah. So in terms of this, in terms of this delta J plane, it's really about what are the states that are big in AdS radius. In terms of AdS radius, I think these states are far here because J basically maps to the impact parameter, or J over M maps to the impact parameter. So there are states far out here that correspond to extended objects in the bulk, very high angular momentum objects. So it's about making sure that nothing funny happens from this corner. So these are the processes which look like this. We have an exchange where this is things are separated by RADS. This is large spin corner.
And so you're saying working at a fixed J suppresses this.
No,
I'm trying to understand how.
no, we don't physically suppress this limit, but we just have to check that our functionals we use remain positive in this limit.
I see.
That's all we have to check.
So
that's the Bootstrap philosophy, right? You don't have to understand the things whose sign you can control.
So you said that the part that you're going to later on say is positive may not be the same as in flat space.
Yeah.
But will be positive anyway.
Yeah. Exactly. So we really avoid this issue of defining a flat space limit of AdS or extracting like people would have thought. I mean, a lot of people tried before to like you start from a CFT and then you try to take some family of CFT and define an S matrix, and then you can apply it to S matrix Bootstrap. Right. Right, it's a naive way of doing the S matrix, of defining the S matrix bootstrap is to first define an S matrix and do that. But what we actually do is we just really cut this middleman. We go from the CFT bootstrap to the S matrix bootstrap without defining an S matrix.
I see. So sorry, I mean, just the way you said it, that this large J stuff would be, the stuff that might spread, and that's what you want to control. That seems like you're making a statement at the level of primaries, right?
Yeah.
But you could have, let's say, light particles, and they can be far away. In that sense, it's the descendant, a large descendant of those light guys that is being an issue. So,
yeah,
should I not worry about that, or everything is
no,
taken care of representation theory?
Yeah, I think everything we do is at the lower conformal block. So I think talking about the primary is enough. Yeah. And the approximations I described work for the.
You can see, right? That physically a light particle can also cause issues because it can get propagated at very large distances just because it is a large angular momentum mode.
Mm-hmm.
How does that? I mean, how is this physical issue being addressed by representation theory? Maybe it is. Maybe just that. Maybe this large distance physics is an image of short distance physics because of representation theory.
Yeah, part of it is if you just have one exchange, three-level exchange, the imaginary part kills it. So the imaginary part at large impact matter is just 0. You need to square it and go to a one-loop process. So some of the issues you're describing here come from accounting for EFT loops. But just the fact that we're taking the imaginary part of amplitude kills a lot of these subtleties also at the leading order. But
I'm not necessarily worried about loops, but just even level.
Yeah, but at 3 level, this process where particle give you a long-range force, it does not have an imaginary part, so does not contribute to the commutator square.
See, you're going to get a left-hand side and a right-hand side. If I understand right, the right-hand side will be the contribution to these heavy guys.
Yeah.
And the left-hand side is...
The left-hand side will be a process with a small impact parameter. So automatically, it's not sensitive to this long-distance physics.
But is the claim that the left-hand side is exactly the EFT expansion of the S matrix, or there's some correction? I'm worried because you're saying that the right-hand side is not exactly what you would get from the S matrix.
Yeah, okay.
So how could the left-hand side be exactly?
Yeah. No, there was a... Yeah, I think the situation we studied in the paper, we assume the cleanest setup is you have a gap here, you don't have this tower stuff. And in this situation, the cutoff has to do with the value of p-perp. Yeah, so p-perp was enough, p-perp was enough to make this look more and more like flat space.
Okay, so then in this limit, the right-hand side must also be what you get in flat space, or not? In this limit, that p-perp is taken very large.
Yeah, both the left-hand side and right-hand side match the flat space up to 1 over p-perp correction. Which is why it actually, you see conceptually it pays to have wave packets that are dominated by larger p-perp. So this whole concept of expanding around p-perp equals 0 forward limit is orthogonal to the physics there. Okay.